Hello everyone, my name is Eric Timmons, and I'm here today to talk about the Common Lisp Project Manager, or CLPM. To begin, let's talk about it in broad terms. CLPM is yet another language-specific package manager. In fact, it was formerly known as the Common Lisp Package Manager before I came to my senses and realized that I didn't want to cause any confusion between packages as a collection of symbols and installable units of software. It manages dependencies for and is implemented in Common Lisp. It is able to take the place of the Quick Lisp client and interfaces seamlessly with both ASDF and the primary Quick Lisp distribution metadata. I am currently a graduate student in a university research group, and I created it because I was frustrated with the status quo of Common Lisp dependency management. Our group is a loosely coupled team with high turnover rate as students enter and then graduate. Ideally, all of our software would always be backward compatible, but in practice, things have moved quickly enough that it's often difficult to reproduce demos, which are important for funding, in any sane manner. Additionally, bringing new students up to speed on Common Lisp was hard enough without also having to introduce them to a dependency management tool that was unlike anything they had ever used before. So, what are some of these killer features that CLPM brings to the table? First up is HTTPS support. All of my group's code is stored on a server that requires authentication, and I do not want credentials to be sent in the clear. Second is the ability to reason over version constraints on dependencies. This allows us to mark lower and upper bounds on the version of a system. Third, CLPM can install dependencies locally to a project or globally for a user account. This makes it possible to do things like reproduce old demos using old versions of code, while still being able to develop the latest and greatest version as well. Fourth is the ability to completely replicate a context from scratch on another machine or on the same machine at a later time. Fifth, CLPM has an executable with a complete command line interface that can be trivially installed. I use this primarily for CI/CD purposes, but it can also help ease the transition for students that aren't used to image-based development quite yet. Last, CLPM has the ability to install dependencies directly from source control. This allows you to track changes to your dependencies before they've been officially released. There are some other dependency management solutions out there for Common Lisp that provide some bits and pieces of this, but to my knowledge, there's no solution that provides all of them. To make my life harder, I also decided that I would operate under a few constraints that eventually became some of the guiding philosophy for this project. First, CLPM tries to build on existing libraries where possible. I don't want to reinvent the wheel. Second, even though a big draw of the command line interface is to provide a familiar environment to people coming to Common Lisp from other languages, I want to make sure it's not at the expense of sacrificing interactive, image-based development. Last, I want to place as few constraints on the developer workflow as possible. Everything should be configurable by the user. I don't want to require a complicated runtime environment, and if a project uses CLPM, the consumers of that project shouldn't have to care. Now that we've talked a bit about what CLPM brings to the table, let's take a step back and make sure we're all on the same page regarding exactly what's involved in dependency management and what the current de facto approach is. While some of this section may be relevant to other programming languages, we're going to focus on Common Lisp and ASDF as a build system. First, let's talk about terminology. A project is the primary development unit of code. It typically corresponds to the contents of a single version control system or VCS repository, such as a Git repo on GitLab, GitHub, wherever you like. A release is a snapshot of a project. It is typically identified using a version number, date, or VCS commit identifier. A release may contain multiple systems, and systems are defined via ASDF's def system. It describes components, which are typically source code files to be compiled and loaded, the version of the system, and dependencies on other systems. What's a dependency? A dependency, for our purposes, is a tuple, FSV, where F is a feature expression, S is a system name, and V is a version constraint. It states that if feature F is satisfied when evaluated against the feature's special variable, then a system with the name S is required whose version satisfies V. A source or an index is a collection of project and system metadata. And last, a context is a set of dependencies and releases that satisfy them. Any complete dependency management setup must perform 3 tasks, at least. First, it must resolve dependencies. This step is all about taking a list of dependencies and creating a list of releases that satisfy them. For example, we may have some demo system, CLPM demo, that depends on the system 5am. Resolution may choose the January 4th, 2021 release of the 5am project to resolve it. Then that version of the 5am system is examined, and it has dependencies as well. In this case, Alexandria, ASDF FLV, and trivial backtrace. This is a simple example, but you can imagine how it can get complicated the deeper the dependency tree is, and if the dependencies actually have version constraints as well. Next, the dependencies must be installed. This typically takes the form of downloading release tarballs, verifying them, unpacking them, and configuring a system like ASDF to find them. Last, the dependencies must be built. ASDF will compile and load every source file in the correct order for us. Now let's look at the current state of the art and how it is architected. On the left, you'll see a developer's Lisp image. This image contains ASDF and the Quick Lisp client. Typically, the developer interacts directly with Quick Lisp by quick loading the system. When a system is quick loaded, it and its dependencies are resolved, installed if missing, and then the Quick Lisp client uses ASDF to load them. Resolution happens entirely in the Quick Lisp client, using both metadata provided by the Quick Lisp project index, fetched over the internet, and signals from ASDF about missing systems, for example, if the metadata is incomplete. Installing also happens entirely in the Quick Lisp client. This means that for interactive development, your image needs to contain all the code for every dependency management task. Note that while this Quick Lisp-based setup is almost certainly the most widely used solution, there are other alternatives as well. The one most similar to CLPM is called QLOC. I'm happy to talk about QLOC comparisons in the post-talk discussion, but for time's sake, I'm going to focus on comparisons to the de facto solution during the rest of this presentation. Now let's begin to dig into CLPM in earnest. First, let's look at how CLPM is architected. This diagram shows how CLPM is typically used during interactive development. The first thing you'll think is probably, whoa, that's a lot more complicated. I hope to convince you by the end of this talk that while it may look more complicated, this design actually lends itself very well to separation of concerns and modularity. A few things I want to draw your attention to. First, the developer largely interacts directly with ASDF. The CLPM client then integrates with ASDF to run only if it is needed. Second, there are other processes involved in the architecture, namely the worker and the groveler. The worker is the only one that actually needs to communicate with the internet. Third, notice that project metadata can come from either a Quick Lisp distribution or another source designed as part of this project, called CLPI. While a common Lisp developer spends most of their time doing interactive development, it is important to consider non-interactive use cases as well. For example, running CID scripts in a clean environment. On the left is how CLPM works during non-interactive resolution and installation. No development image is needed. On the right is how CLPM can be used to non-interactively assemble a Lisp image. The worker simply configures some environment variables for ASDF before spawning a common Lisp process. The CLPM client is not needed at all in this case. Now let's review the 3 major components of CLPM and what they are responsible for. First is the worker. As I've already said, the worker runs in its own process and is actually distributed as both source and a precompiled executable. The worker performs all resolution and installation tasks. Second is the client. The client is written in Portable Common Lisp and is really only needed to manage interactive development. Third is the groveler. This is an internal component of CLPM that users should never need to interact with directly. It is responsible for extracting system dependencies and metadata from local projects or releases directly from VCS. One of the, we'll call it features of ASDF systems, is that even loading a system definition can result in the execution of arbitrary code. In order to prevent this development image or the CLPM worker from entering a potentially broken state, the groveler runs in a completely separate process. Additionally, there is currently some experimental support for sandboxing the groveler. The components communicate with each other by passing S expressions through a REPL, and as a simplified example on the right shows. Why is CLPM architected this way? There are many benefits, but there are three that I consider the most compelling. First, the most complicated component, the worker, can freely use dependencies. This includes both common Lisp dependencies and foreign library dependencies, such as libSSL. This lets CLPM build off the efforts of the entire common Lisp community without interfering with the user's development image. This interference can come in many forms, such as version mismatches, package nickname clashes, or even image size. Second, only the groveler and the client need to be portable. This allows us to focus our efforts on 1 to 2 implementations for the worker and know that all the features we need will be available. Right now, CLPM currently targets SBCL for the worker. This is because it has broad CPU and OS support, it is very capable and performant, and by using an out-of-tree set of patches that I've developed, we can use it to build static executables for Linux. CLPM will likely target ABCL next, due to the ubiquity of the Java virtual machine. Last, this architecture makes it trivial to perform dependency management tasks from a REPL or other processes such as bash scripts. I said previously that CLPM can manage dependencies in both a global and project local context, or bundle. So what does that mean? First, global contexts were largely inspired by Python virtual environments created with the virtual env wrapper script. Bundles are largely inspired by Ruby's bundler and Common Lisp's own QLab. Global contexts are identified by a string. Bundles are identified by a path name, typically to a file named CLPM file. Global context information is stored in the CLPM data directory, typically under the user's home directory. Bundle information is stored in both the CLPM file and a lock file called clpm-file.lock, creatively enough. Bundles are designed to be both relocatable and contain additional configurations specific to that bundle. One last feature of global contexts is that much of their information can be written to an ASDF source registry file so that after the resolution and installation is complete, CLPM is not needed at all to build anything in the context. While these are both useful, I will be focusing on bundles for the remainder of the presentation. Before finally getting to examples, let's discuss where CLPM can retrieve project metadata. CLPM is compatible with official QuickLisp distributions, such as the primary one at beta.quicklisp.org. While the QuickLisp client itself does not have the ability to use HTTPS, it turns out all the metadata and release tarballs are served over both HTTP and HTTPS. Simply enter an HTTPS address to have CLPM use it. Unfortunately, there is no real specification for a QuickLisp distribution, so your mileage on others may vary. For instance, CLPM does not currently work with UltraLisp because UltraLisp does not publish a file containing a list of all of its previous versions. While CLPM is compatible with QuickLisp dists, those dists do not contain all the information CLPM can use. This includes system version strings, version constraints for dependencies, and upstream VCS information. Additionally, due to the way QuickLisp distributions are structured, CLPM has to download every metadata file to ensure correctness, which can be slow. An offshoot of the overarching CLPM project is the development of a new project index, called Common Lisp Project Index, or CLPI. I maintain a mirror of the primary Quick Lisp metadata in this format at this address. CLPI was designed to include all the information that CLPM can take advantage of, plus the format is extensible, and due to a combination of serving a multitude of files and specifying that most of these files are append only, metadata can be efficiently, lazily synced. While I run a CLPI server for my research group that contains all of this extra metadata for our internal code, CLPI has not seen as much battle testing as the Quick Lisp metadata format, unfortunately. Now that we've covered how CLPM works and why it's architected the way it is, let's turn to practical examples of using it. Tarballs and installers can be found on the CLPM website. I will not go through the detailed installation steps here. For that, see sections 6.1 and 6.2 of the paper. Additionally, I have made a simple example project called CLPM Demo located in this repository. The remaining steps assume you have the ELS21 branch checked out somewhere. And if you go to install CLPM, I will note please use the latest version in the 04 series, even if it's alpha. The full 04 version will be coming out soon as I get a build on Apple Silicon. Before continuing, I always find it's important to know what files will be touched before you start running a program. In addition to any bundle-specific files, CLPM will look in these locations for its configuration, cache, and data storage. Right now, configuration is read-only, but I hope to add commands so that you can interactively modify the CLPM configuration. The first step to using CLPM to manage project local dependencies is to create a CLPM file. These files are simple enough to create by hand, but you can also have CLPM do it for you. Evaluate this form to create a CLPM file located at the provided path. The ASDs argument specifies which ASD files the rest of the dependencies should be extracted from. After evaluating this, you should have a file that contains these forms. Let's take a moment to dig into a CLPM file and its contents. A CLPM file is meant to be written by a developer to describe the project-specific bundle they want. Each CLPM file must begin with a version statement. This allows the file format to evolve while still providing some amount of backwards compatibility. The next entries must describe the indices from where the developer wants to install dependencies. In this example, we're using only the primary Quick Lisp distribution. Note how each directive is simply a plist. This makes extensibility easy and makes it trivial for any other common Lisp program to parse the file. The next set of directives must describe the dependencies of the bundle. Typically, a CLPM file need only contain a dependency on a local system. This example says that all of the systems contained in superawesome.asd must be part of the bundle, as well as the dependencies. While this is ideally all that is needed, a developer can add additional dependencies to the bundle as well via the CLPM file. For example, a specific system can be added, an entire project can be added, or a requirement that a specific project be installed from source control can be added. Now, let's go back to our REPL. Before you can start using this new CLPM file you've created, you need to actually install the dependencies. You can do this using the install function of the CLPM client. As you do not have an active context yet, you need to specify the context. And when specifying a bundle as the context, it is required that you use a path name, not just a string with a path, but an actual path name. After evaluating this, you will actually be dropped into the debugger, with a message similar to this. CLPM tries to not modify contexts without explicit consent from the developer. Therefore, the client signals a condition before the worker can perform any changes. Invoke the approve diff restart to actually commit this information to the lock file and install the dependencies. Once you have a lock file, you can activate the context by using the activate context function of CLPM client. Evaluate this form and then load the system, and you'll see that hopefully everything will be loaded successfully. Now, if you actually go and take a look at, dig into the CLPM demo code, you'll see that there's a test.lisp file that has a test suite defined using 5am, but if you look at the CLPM demo test system definition, we forgot to declare 5am as a dependency. We can fix that by adding 5am to the depends on list for the CLPM demo test system. Now, if we try to run a test with ASDF, we'll quickly run into a problem. We don't have 5am installed. This is the perfect time to use the re-resolve requirements and reload config restart. It will notice the new dependency and ask you to install it. Accept the diff and watch the tests pass. Now, let's say you decide that there's a feature in 5am's Git repository you want to use, but it hasn't been released to QuickLisp yet. No worries. Add the following to your CLPM file, then reinstall the context so it gets the new dependency. And this diff will then show you that CLPM is changing from a released version of 5am to a specific commit from the Git repo. If you retest the CLPM demo system now, you'll see that it recompiles 5am using files from a different location. Last, let's say you want to add a feature to 5am and want to use a local copy of 5am in your bundle while you develop it. This can be accomplished by cloning the 5am repo next to the CLPM demo folder and adding the following to the bundle.conf file located at this path. This tells CLPM that if it encounters a VCS requirement for 5am, it should be satisfied using the repository located at this location relative to the CLPM file. Reinstall the context so that it gets the new override. Unfortunately, in the current diff format, you won't see an entry for this change, but you still need to approve it for the change to take effect in the current session. This will hopefully be made more clear in version 0.5. It's worth noting that using this feature requires great care. If you commit a version of clpmfile.lock that references a 5am commit that you have not pushed, all of your collaborators will have a bad day and blame it on you. And this concludes our whirlwind tour of CLPM. Hopefully by this point I've convinced you that CLPM brings some useful features to the Common Lisp ecosystem and is architected in a fairly sane manner that leaves a lot of room for new features to be added while sticking to our guiding philosophy. As with many projects, the work on CLPM never ends. In addition to the standard adding more tests, which are very much needed, and splitting out individual capabilities that I've designed for CLPM into standalone libraries, I'd really like to work on the following tasks. First, versioning and version constraints are a pretty central focus of CLPM, and I think more can be done on this front in the Common Lisp ecosystem at large. I'm currently working to propose capabilities for more expressive version strings and constraints and integrate them into ASDF. Second, I'd like to add more worker-client communication methods. This could lead to interesting architectures, such as persistent worker processes, or worker processes that are Dockerized or otherwise isolated from other processes on the system. Third, I'd like to look at installing scripts to a developer's path when installing projects. This could let you use command line tools provided by some of your Common Lisp dependencies as well. Last, I really need to ruminate on the future of CLPI. While I think the extra metadata that CLPI exposes is super useful, I don't want to maintain a CLPI server for the whole Common Lisp community by myself, other than a simple mirror of QuickLisp's metadata. So I either need to work with Zach to fold the lessons learned from CLPI into the QuickLisp metadata format, and or find a group of people willing to run a CLPI service with me. And that concludes my talk. Thank you for your time.